Hello everyone. In today's video, we are going to discuss about one of the important combinational circuit, that is a multiplexer, or simply you can call it as MUX, MUX. So in this MUX, there are different types of multiplexers. One of them is 2 cross 1, and the second one is 4 cross 1, and the third one is 8 cross 1, and there are many of them. So in today's video, we are going to discuss about the simple and the basic one, that is 2 cross 1 multiplexer. As you can observe here, one of the common point here is output is only one line. So as I can tell you, a simple definition of multiplexer is nothing but a multiplexer is a combination circuit which has many input lines and only one output line. So I can draw a block diagram for you and I can show you. So this is a block diagram. So this is our MUX. It may have many input lines, but there is only one output line. So how does this multiplexer know which of this input should be the output? So for that purpose, there are few other lines. Those are called as select lines. So how does we know how many input lines are there or how many select lines are required for these input lines? So for that, there is a formula or a general expression for a multiplexer. So 2 power n cross 1 is a general expression for multiplexer, where n is number of select lines. That is, for example, now I am going to discuss about 2 cross 1 MUX. So 2 cross 1. As you can see, 2 power 1 is 2. That is, we are going to require only one select line. So the block diagram for 2 cross 1 multiplexer would be two cross 1 MUX. As I have told you earlier, there are two inputs. So 1, 1. So I am naming them as D0 and D1. That is data 0 bit and data 1 bit. And I am indicating the output as Y, or representing the output as Y. So 2 power 1, that is one select line. So there is one select line. So this is the basic block diagram of a multiplexer. So next, I am going to discuss about the truth table of the multiplexer. A simple truth table, then I am going to expand it. So S and Y. So as I have told you earlier, how does the multiplexer know which input should be connected to the output? So for that purpose, as I told you, select lines are used. So how does this select line tells you which input should be connected to the output? So when select line is 0, the output would be D0. When select line is 1, output would be D1. So from this table, we can derive the Boolean expression for the multiplexer. That is, Y is equal to 0 S bar and D0 plus S1. So only because it is not a 0 value, it is 1. Hence we are going to directly write it as S, and here is the D1. So this is the basic or the Boolean expression for 2 cross 1 multiplexer. So when I expand this truth table, as you know, D0 and D1, these are 2 bits. Hence 4 combinations are possible: 0, 0, 0, 1, 1, 0, 1, 1. So now I am going to show you when S is 0 and when S is 1, how would be the output when these values are considered. So I am taking the truth table S, D0, D1 and Y. So as I have told you earlier, S and Y, when S is 0, Y is D0, when S is 1, Y is D1. So when select line is 0, 0, 0, 0, 1, 1, 0, 1, 1. So as I have told you, when S is 0, output would be D0. That is, we are not going to consider these values, or these values would be don't care condition. That is, when S is 0, directly the output would be the values of D0. 0, 0, 1, 1. And in the same case, we are going to consider S as 1, same 0, 0, 0, 1, 1, 0, 1, 1. So the values would be, when S is 1, output is D1. That is, when S is 1, output would be the values of D1. 0, 1 and 0, 1. So when I again simplify this table, S, D0, D1 and Y, when I simplify this table again, I will again write and show it to you. S, D0, D1 and Y. When S is 0 and D0 is 0, either when D1 is 0 or D1 is 1, output will be 0. As I told you, when S is 0, output is the value of D0. So in the same way, when S is 0 and D0 value is 1, when D1 is 0 or 1, the output would be 1. That is the D1 value. Hence, we can directly write it as don't care X, X. In the same way, when S is 1, when D0 is 0 or 1 and D1 is 0, when S is 1, Y would be the value of D1. Here the value of D1 is 0. In the same way, when S is 1, when this is 0 or 1, when D1 is 1, then the output would be 1. That is the D1 value. Hence, you can write it as X, X, 1. So this is the basic truth table representation of a 2x1 multiplexer. So now we know the Boolean expression for a 2x1 MUX, that is S is equal to, Y is equal to S bar D0 plus S D1. So now we are going to represent the 2x1 MUX using a logical circuit or logical representation of 2x1 MUX. So I am going to draw the diagram. Sorry if my diagram is not neat. So as we can see here, S bar dot D0 and S dot D1. That is, we are going to require one AND gate here and one AND gate here. That is, two AND gates are required and there is a plus symbol here, that is an OR gate. Hence we are going to require two AND gates, one OR gate, but we have S bar here, that is one NOT gate is also required. So now we are going to represent the MUX using the logical gates. Simply to say, we are going to build a 2x1 MUX using a basic logic gates. Just a minute. So the logical diagram would be, as I have told you, two AND gates, one OR gate and one NOT gate is required. So AND gate, AND gate. So I am connecting here D0 and I am connecting here D1. But when you see the expression S bar D0 plus S D1. So D0 has S expression and D1 is also having an S expression. That is, the AND gate is combination of D1 and S. This AND gate is combination of, this AND gate is combination of D0 and S bar. This AND gate is combination of D1 and S. So now we are going to completely draw the AND gate. So first D1 is having S. So I'm taking S here. So this is directly connected. Since there is no NOT gate or there is no bar here, directly S is connected here. And when we consider D0, S bar is there, and hence we are going to connect a NOT gate here. So this would be S bar and this is only S. So now finally we are having an OR gate here. So this output and this output is connected to a OR gate. So this is the logical diagram for 2x1 multiplexer. Thank you.